We're going to continue looking at systems of linear equations, but here we're going to have more than two variables. You can have an n number of variables. We're only going to be looking at systems with 3 variables, but linear equations can have as many variables as are necessary to model whatever they're supposed to model. We're going to look at systems that are linear, so everything just has an x term, a y term, a z term. None of the variables are going to be squared or square rooted or anything like that. Everything is linear. So solving a system of equations involving 3 variables is a few more steps than just 2 variables. So if we have a system of linear equations, here's a system here, you can see that each one of these has 3 variables. They each have an x term or a y term and a z term, and then a constant over here on the other side of the equal sign. If we have a triangular system or the triangular form of a system, it's much easier to solve these systems of equations. We automatically start off with a value for one of the variables. One of the equations is only in 2 variables, one of which is the one that we know the value for, so we back substitute here. We would find a value for y, and then the third equation that had all 3 variables in it, we would back substitute for y, back substitute for z, and find the value of x. So when we have a system that looks like this, we take steps to eliminate by pairing a couple of equations in a couple of different equations to eliminate variables and turn it into this triangular form so that we can actually solve it. First, we will solve one that's already in triangular form, so you can see how easy that is. So from the last equation, we know that z equals 3. We take z, substitute it into equation 2, and we find that y equals -1. When we have the value for y and have the value for z, we substitute that into the first equation and find the value for x. Now we have a line in 3 dimensions that has coordinates 2, -1, and 3. So there are 3 lines in space, in 3-dimensional space, that intersect at the point 2, -1, 3. To change a system of linear equations to an equivalent system, that is a system with the same solutions as the original one, we use the elimination method. And so we can follow the following steps. We can either add a non-zero multiple of one equation to another, we can multiply an equation by a constant, or we can interchange the positions of 2 equations. So to solve a linear system, we use these operations to change the system to an equivalent triangular form and then use back substitution like we did in example 1. This is called Gaussian elimination. So let's use Gaussian elimination to take this system and put it into the triangular form so that we can solve for the variables. So we need to change this to the triangular form. And what we're going to do is we're going to take 2 equations and we're going to eliminate one of the variables. We can see from our system that we have 2 equations where the coefficient of x is 1. So it's very easy just to eliminate one of those variables. So we're going to take this one and we're going to subtract the second one. We're used to adding them, but here we're going to subtract. So x minus x is 0, 2 minus -2 is 4, -1 minus 3 is -4, and 13 minus 1 is 12. So we can add or subtract either way. We could also take one of these and just multiply through by -1 to change all the coefficients and then add them. So if you're addicted to adding these equations together, then you can go ahead and multiply by that value and make sure that the coefficients have the same value but opposite signs. Here all that's been done is that we've subtracted them. So now instead of 3 variables, now we have an equation in 2 variables. And so we have changed equation 2 to equivalently look like this. So we put equation 1 back where it belongs, we change equation 2, and now we're going to try to take these other 2 that have an x in them, and we're going to try to eliminate x out of those 2. So we put those 2 together, we make the changes that we need. We multiply the top equation by -3, and then we add, so we come up with 8y minus 14z equals 0. Now we have two equations in in two variables. And so we're going to do the same thing and try to eliminate either y or z so that we get one equation in one variable. So we take these two, if we multiply this equation by -2, that gives us -8y plus 8z equals -24, and we can add those together and we can see that z would then equal 4. So we have z equals 4, then we have an equation in two variables, so now we can solve for y, and when we know the value of z and y, we can substitute in and find the value for x. So that's what we're going to do. Z equals 4, we substitute that in here, we find that y equals 7, we substitute 7 and 4 into the top equation, and we find that x equals 3. So again, there is one ordered triple, one point in three-dimensional space where these three lines intersect. So there's Gaussian elimination. Come to class next time and we'll solve systems of equations that involve three variables.